All right, welcome back. In the last video, we just started section 1.1. In this video, we'll continue working on it. We're going to begin by evaluating some more functions. So in this one, we're evaluating a function given its graph. So here, this is a picture of a function g that we're working on. We want g of -4, g of -2, g of 0, g of 2, and g of 4. Remember that what's going into the parentheses is an x value, and we want to know what the corresponding y value is. So g of -4, taking a look at the graph, each dot is worth 1. So we're here at 0, 0. We'll go left 1, 2, 3, 4. G of -4 looks like it's 3. Make sure that you can tell how I did that. If you're not sure and can't figure it out, let me know. G of -4 is +3. Let's try the others. You may want to pause the video and try this on your own, and then check your work against what I've got here. Okay, G of -2. Here's -2. We'll go up to this point. It looks like there's a y value of 2 there. G of 0, when we're right at the origin, the x is 0. We'll have to go down to -2 to find our y value. For G of 2, when x is 2, our y is equal to 1. One interesting thing happens on the graph right here. If you had any doubt, is it 1 or is it 3? You'll notice on the graph that at the lower part, it's a filled in circle. At the upper part, it's a hollow circle. That indicates that the function is defined to be 1 right at that point, not 3. It is true that f of like 2.1, sorry, it's g, isn't it? G of 2.1 is a little bit under 3. It's like 2.9 something, right? If you go just to the right of 2.1 of 2, you'll be on this piece of the curve. So it's pretty close to 3. If you were at G of 1.9, it's going to be pretty close to 1. So it's probably like 0.9 or something. Okay, G of 4, finally, that's going to equal 0. When we have an x value of 4, we'll have a y value of 0. You want to make real sure that you can distinguish between the G of 0 equaling -2 and G of 4 equaling 0. In the first one, the input is a 0 and the output's -2. In the second one, the output is a 0 where the input is a 4. Okay, we're going to skip over B because we haven't done domain and range yet. Here in part C, it says find the values of x for which g of x is equal to 3. So here, we don't want to put in an x of 3, right? Here, we don't know the x. It says find the x. We want to find the x so that the output will be 3. So where's the output equal to 3? Okay, there's where the output is 3. You want to be very careful here because there's only one spot, right? At 2, we know the value is 1. So there's only one place, and that's -4. So it's only -4. Okay, next step, we want to estimate the values of x for which g of x is less than or equal to 0. So where could that be? The g of x's are the outputs for the function. So where are the outputs less than or equal to 0? Remember, less than or equal to 0 is below the x-axis. Where's the graph below the x-axis? It's between -1 and looks like about 1.8 maybe. Maybe -1 to 1.8. Let's see, that was D. -1 to 1.8. I'm guessing there, right? It said approximate or estimate. Here also I'm using interval notation. If that's rusty for you, we'll be reviewing that here in the next section as well, in 1.2. Find the net change in G between x equal -1 and x equal 2. The net change in a function is just the difference of its function values. So we'd have G of 2 minus G of -1. What's G of 2? G of 2 is 1. G of negative 1 is 0. And so we'll just have 0. We have 1 rather, sorry. Okay, so you want to make sure and practice and get better or good at reading values off of a graph. Okay, we'd mentioned the vertical line test before. I wanted to go into a little more detail about that. So what this is learning how to tell if you're dealing with a graph of a function or not. So for a function, each input corresponds to a unique output. Graphically, this gives us the following test. On the left side, you see that if I were to draw a vertical line anywhere in this graph, it's going to cross through the graph at most once or only once. Whereas that's not true for the function or the graph on the right. For the graph on the right, for an x value of a, there are 2 different y values. For the graph on the left, when x is a, the only y value to choose from is b. In general, a curve in the plane represents y as a function of x if and only if no vertical line crosses the graph more than once. An example of a graph of a function would be y equals x squared, which is a parabola with its vertex at the origin and opening upward. A graph of a relation that's not a function would be x equal y squared, which would be a parabola that opens sideways. In this case, there's a lot of different places where we could draw a vertical line through the graph and it would cross more than once. And that would make it not a function, which makes sense. If you think about it, if I told you that x was 16 and 16 was equal to y squared, what could y be? Well, y could be either 4 or negative 4, right? There's 2 different possible y values for that one x value. Okay, and that would make it not a function. In general, if you cut through a graph with a vertical line and it crosses more than once, it's not a graph of a function. Notice that it doesn't have to be true in every place. For the function on the right, I could draw a line right here that crosses through it only once, but still overall the graph is not the graph of a function because there is at least one place where it's messed up. That is, crossing it with a vertical line will cross more than once. Okay, vertical line test. Usually the results of vertical line test is either yes, it's a function, or no, it isn't. Really, there's not really a lot else to say about that. Okay, another attribute of functions that we're interested in is the idea of a function being one-to-one. So in symbols, what it means for a function to be one-to-one is if the outputs are the same, that is x1 and x2 are 2 distinct x or 2x values. If f of x1 equals f of x2, then it must really be that x1 and x2 are the same. And this is kind of a math, almost fancy way of saying if you have 2 functions whose outputs are the same, then their inputs are necessarily the same, or that there are no repeated y values. In order for a relation to be a function, it had to not have repeated x's. One-to-oneness is stricter. For a function to be one-to-one, it has to be have the property that the y values can't repeat, in addition to having the x values not repeating. So several ways of saying that. The y values don't repeat. If x1 and x2 are different, that is, if you have 2 different inputs, then you'll have 2 different outputs. Or if you have equal outputs, you'll have I have that backwards. Sorry, there's a little typo in here. Let me fix that. Hold on a second. Sorry about that. There was a missing mark on there. This first, what was an equal sign should be a not equal sign because we need the outputs to be different whenever the inputs are different. So sorry about that. All right. So in short, probably the easiest way to think about that is that there are no repeated y values. Okay. So we want to decide in each case for these if each function is one-to-one. So are there any repeated y's? 2, 1, 5, 3, 8, 16. So there are, of course, no repeated x's because it's a function. Additionally, there are no repeated y's, so this thing is 1 to 1. Okay, for B, 1, 5, 2, 3, 6, 5, and negative 1, 8. It looks like there are repeated y's, specifically the 5s, so this is not 1 to 1. And then the reason why is, of course, it's the 5s. Okay, functions given by tables, 2, 5, 1, 0, 3, 7, and 8, 0. I see a couple of repeated y's there, so no, it's not 1 to 1. For the other function, there's no repeated y's, so yes, this would be 1 to 1. Okay, a couple of functions given with arrow diagrams. In order for a function to be 1 to 1, we can't have repeated y values. So taking a look at the y side, are there any values of y that are targets of 2 arrows? So it looks like this value of 8 has 2 arrows that lead to it. When x is 1, y is 8. And when x is 9, y is 8. Right? So this thing is not 1 to 1. In order for a relation to be a function, we can have one arrow leaving the x's. That is, each x is used only once. In order for a function to be 1 to 1, each y can have only one arrow leading to it. Okay? Here for f, each x value has only one arrow leading away from it, so it's a graph of it, or it's a function. For the y's, each y value has only one arrow leading to it. So this makes it 1 to 1. If you have a function that's 1 to 1, it's predictable in both directions. Given an x, you can know the y because it's a function. And if it's 1 to 1, if you are given the y, then you can recover what the x was. We'll do more on that later in the chapter when we talk about inverse functions. Okay, so this kind of summarizes a bit of what we just talked about. In order for a relation to be a function, no x values can be repeated. If additionally no y values are repeated, then it is a 1 to 1 function. So this is kind of a Venn diagram of our situation. There's all these relations. Anytime you write down values of 2 variables, you have a relation. If you have that requirement about the x values not repeating, then you have a function. If additionally the y values don't repeat, then it is not a function, then it is a 1 to 1 function. If you have a relation that is not even a function, like that, 2, 1, 3, 2, let's say, this thing is not even a function. Y is not a function of x. We wouldn't even discuss whether it's 1 to 1 or not, because the 1 to 1-ness is a property only of functions. Okay, so it's just not a function, and that's the end of the story. All right, so we are almost done with this. Like we had a vertical line test to tell if a graph was a graph of a function or not, we have a horizontal line test to tell us if we're dealing with a graph of a 1 to 1 function. For a 1 to 1 function, y values can't be repeated, right? So if you have a graph here shown in blue, if we have this red line, that is basically like saying, okay, well, we're specifying a value of y. If we specify a value of y and it crosses the graph more than once, then that's saying, okay, well, here's these 2 x values that belong to that y. And specifically, it's not going to be a 1 to 1 function because f of x1 is equal to y, and f of x2 is also going to equal y. In other words, that particular y value is repeated, making it not a 1 to 1 function. The vertical line test was a way of giving an x and seeing if you had multiple y's. The horizontal line test is a way of giving a y and seeing if you have multiple x's. All right, so let's try it on these couple of functions. All right, so for this kind of first really curvy one, I can see definitely there's a spot where this thing is not even a function, right? If you take a look, looks like there's this vertical line that goes right through there that crosses a few times. And so that thing is not even a function. So we're not even going to talk about whether it's 1-to-1 or not. This next one looks a little like a serpent, kind of. This one, no vertical line will cross it more than one time, but there are definitely places where a horizontal line will. So this is a function, but not 1-to-1. And then the last one is a 1-to-1 function. If you draw any vertical line you want through this graph, it'll cross the green line only once. If you draw any horizontal line through it, it'll cross through the graph only once, making it both a function and 1-to-1. All right, so we just have 2 slides left for this section. The last part is our book features a couple of kind of commonly used functions. There's first of all, a constant function, which, as the name implies, that means that the values of the function never change. In this case, it's f of x is equal to 2. No matter what x value you plug in, you're going to get a y value of 2 out. F of x equals a constant. The identity function, no matter what number you plug in, you get the same number out again. Notice that the graph of this is going to be a line with slope 1. If you look at that and think y equals mx plus b, that is a line with slope 1 and y-intercept 0. And sure enough, that's what we have as far as a graph goes over here. A line with slope 1 and y-intercept 0. Absolute value graph, we'll talk more about this in section 1.2. And later, there's a whole section devoted to these. But this is basically a V-shaped graph with its kind of corner point sitting at the origin. We've already used the quadratic function today, that's x squared. It's basically this U-shaped graph with vertex at the bottom. A cubic function, x cubed, has this kind of quadrant 1, quadrant 3 picture, and it has 180-degree rotational symmetry around the origin. Okay, one more page of these. We have a reciprocal function. This is a function, our first function that is undefined someplace. This one, if you try to put in 0, you don't get a value out. 1 divided by 0 is undefined, right? So there's a break in the graph right there where that occurs. The rest of the graph occurs in quadrants 1 and 3. The reciprocal function squared, 1 over x squared, has its picture in quadrants 1 and 2, but is still undefined at 0. Our square root function has its graph only occurring in quadrant 1. And then the cube root graph has a little bit of a resemblance to the x cubed graph, but it's what's called concavity is different. Instead of opening upward in quadrant 1 and then downward in quadrant 3, the situation is reversed. All right, so what you want to do with all this, okay, we'll be kind of looking at functions as basically building blocks to make new functions out of. So if you can get used to these, then your work later will be easier if you think about the basic kind of characteristics of constant identity, absolute value functions, and so on. So virtually all the functions that we have in this class are, at least until we start the trigonometry part, they are built out of these functions. All right, so that finishes section 1.1 for us, finally. If you have any questions, let me know, and have a great day.